Okay, no surprise. The next set of slides is on compression. I will preface this with we're not going to go through masonry column compression. Again, walls is the primary use that you're going to encounter when you're out. And you can figure out the column piece pretty directly. I'll go through kind of how it works. We're not going to do an example on the wall for this little section here, so just follow along on this. What we'll do is when the next section will be compression and flexure. And walls are generally going to have both compression and flexure. Right? They're going to be carrying load from above, and they're going to have the flexure component. Um, so pure compression might be a column with basically no other type of load on it, but even then, with load eccentricities and things, usually going to have the two combined, compression and flexure. All right, so just let me go through how this works and what section it's in for our handbook. All right, so it's in 5.4. So if you go to your masonry handbook, it's on page 150, which is 5.4 compression. And the first equations I'm going to go through on the slides are here. Okay? And then we're going to back solve those equations. I need to point out that on the next page, 151, there is a typo in the handbook. So pause now and go fix this typo or mark it or something, or write down that there's an issue, right? So they mean to solve these for F sub A, and they actually wrote P sub A on here. All right. So stress versus force. Okay, so the first set of equations in the handbook show you the maximum allowable, and you're going to do all this in terms of an H over R ratio, and R is the radius of gyration over A. I'll show you they have information about that in the tables. We'll come back to that later, but that's what R is. So the allowable P axial load is going to be this F sub n, F prime n, times AN, and then it's multiplied by a quarter. And that's just a safety factor that they're putting in. Okay, so this is the masonry term, and then this is the contribution from the steel. Okay, so the 0.65 A sub ST F sub S is the compression reinforcement steel. It has to be laterally confined. Okay, so ties. If you want to do a column, you follow these equations and you make sure you have lateral confinement, and it goes through the requirements for ties in the TMS, or you can find that also in the handbook. But we're going to look at walls, and walls, there's not really, they don't typically have that type of confinement, right? It's just a bar every couple feet or whatever, like we've been doing, and there's not confinement around that steel. Because of that, I can't count that rebar for compressive strength. Those rebar are in there for the flexural piece, the tensile piece, right? So when I do a wall, I only use the masonry piece of those equations, which means that if I have unreinforced masonry wall or reinforced masonry wall, because there's no confinement, basically the strength is the same. So the bar is only contributing when I'm looking in flexure. So the next piece of the handbook, rewrite the equations in terms of stress. So the P over A, and this is what those equations look like. And again, just make sure you get that typo in the handbook. It says it right here. So since we're only going to focus on walls, not columns or pilasters, that makes this fairly straightforward because I'm only going to use the masonry piece of this equation. All right, so compression on walls is specifically in 510 of the handbook, so we can skip ahead here a little bit. Which I always have trouble doing. Should have typed in the page, my apologies. Gotta get to the wall section here. Almost there, deep beams. 9 is, so if you want to look at the columns in 5.9, you can go through a column example. It's pretty straightforward. Okay, now walls. So in, wrong thing, 510, we've got the wall piece. A wall is a vertical element with a horizontal length to thickness ratio greater than 3 used to enclose a space. We know what a wall is. Here's my compression equations for walls, and or my stress equations for walls, and you notice that there's only the masonry portion, no steel portion in there, right? So as these equations in your slides, here's R square root of I over A, and the tables in the handbook actually tabulate those values. You can do the I over A, and if you do that out for a rectangular section, you end up with the thickness over square root of 12. You can do that calculations yourself. Thickness, in the case of a wall, the thickness of the wall is our old H when we're doing a rectangular section. So you can derive that, but you don't need to because you can actually use the tabulated values. All right, so you might use that on a column or something. The wall section properties are in those tables in the handbook as well. In this case, the GN6 and the GN16. And net section properties are what we use for, excuse me, strength and strain calculations. Okay, we'll use average for stiffness, deflection type calculations, but for strength and strain, we're going to use net. The slenderness term looks at the stiffness of the member, so we should use an R average when we do that H over R calc. And again, those are tabulated for you. All right, so the compression demand on the wall is the P over A, where A is the demand, F is effective cross-section, okay, which includes the grouted and mortared areas, the filled areas, and I can get those out of the tables. Uniform axial load on walls, okay, we assume a concrete slab or a hollow core plank is going to bear on the top of the walls, and we determine the demand in pounds per foot of length and capacity in pounds per linear foot, as we've done before. When I have a concentrated load from joists or beams, then I determine the effective width of the wall that resists the concentrated loads. And there's a good picture in here in just a minute, both in the handbook and in these slides. You don't take the distribution of that concentrated load over a length greater than the minimum of each of these two things. Bearing plus lengths determined by the concentrated load dispersed along 2-inch vertical, 1-inch horizontal line. The picture will show you this a little bit better. Terminate at half the wall height, or an opening, etc., or the center to center distance between concentrated loads. So what is all this? Here's a good picture that's in the handbook and here that shows you the load, and then here's H over 2 and H and how you would calculate the effective length that I can use. So those two are spaced closer together. Here's to the edge. Here's next to a window. Okay, we'll go through that in an example. All right, I'm going to stop with this on the compression piece, and our example will happen when we combine the two together. And the combination of flexure and axial, just like always, is going to have an interaction piece. Okay, and then that's our last major piece for this masonry.